From the Library of Congress in Washington, D.C.
Good evening. Welcome. Thanks for coming to The Printed Instrument. Tonight's panel presentation is part of our Technophiles mini-series, exploring how technology influences the ways we create, perform, and experience music. I'm Anne McLean from the library's music division. It's great for us to have such a varied audience for this tonight, as we look at this exploding field of 3D manufacture and reality computing. And just for curiosity, how many people in the audience are involved with the field in some way? Anybody? A few? Yeah, great. Great. This is a vast and exponentially growing universe, really an ecosystem of technologies. Our speakers this evening will be showcasing a variety of ways in which the convergence of this fascinating ecosystem is creating new design and restoration possibilities for music creation and restoration. We'll start out with a path connecting the world of 3D with music, an introduction to the field from journalist Andrew Wheeler, and a quick and intriguing overview from Tatiana Janzambova, who is a technology whisperer and product manager at Autodesk. Her current project there is the Memento program, empowering artists, scientists, curators, and others to tell their stories through the digitization of capture reality. Robert Howe is a physician and oboist, currently associated with the PhD program at the University of Connecticut at Storrs, and is interested in the study and replication of early versions of the oboe and saxophone. And you have a treat in store, I won't say what that is. Eric Goldenberg is the co-founder of Monad Studio, a design and research architecture firm based in Miami. You may have seen some of his very sculptural instruments in the press over the past few months. His colleague, Scott Hall, on the end, will demonstrate a new 3D guitar that they have designed together. He's an artist, a sculptor, also an animator, and musician. So let me turn this over to Andrew for a fascinating, very state-of-the-technology look at music and 3D.
Thank you. Can everybody hear me? Is that good? Start with a quote. Victor Hugo wrote, "Music expresses that which cannot be said and on which it is impossible to be silent." It's a real thrill for me to be speaking here at the Library of Congress. You can see there in a nice SketchUp 3D model. This isn't the exact building, of course, but my name is Andrew Wheeler. I'm a journalist, and my beat is 3D technology. For the last two years, I've been covering technologies focused around capturing reality, working with spatial data, and using data to interact with and influence the physical world. I was very pleased and surprised to receive a phone call from Anne McLean to help put together this edition of Technophiles. I had just covered a story about a 3D printed piezoelectric violin from Monad Studios that looked like the type of instrument one of H.R. Giger's monsters would play as it watched the world burn. There it is. Anne and I started talking about the ways in which these technologies are being used to create fascinating new possibilities and very interesting musical projects. We both knew of the amazing work being done at the University of Connecticut using a combination of computed tomography scans, 3D software, and 3D printing. Bringing rare and sometimes damaged instruments back to life is an ongoing story which you'll hear more about from Dr. Howe. I also just began working with Autodesk on a high-level concept called reality computing. This is Real 2016, shameless plug, happening March 8th and 9th in San Francisco. I knew from their amazing software and many interesting cultural projects, including building an online virtual tour of the Smithsonian's collection, that they would definitely have something great to contribute to this panel. While we were brainstorming on the phone one day, I began to think about the relationship between musicians and the inventors of musical instruments. I think it stems from an early fascination I had with inventors. After all, I knew who created the light bulb. Bing. I learned who created the AC motor and enabled AC power. Bing. But it occurred to me that I never even wondered about who invented the piano. It was the first instrument I was lucky enough to take lessons on. Thanks, Dad, right there. But I never thought about who invented it, right? It's a strange thing to think about. So then I tried to imagine an alternate universe where the piano was never invented. I thought about things like, well, what would Beethoven's Moonlight Sonata have sounded like? And how would it have been delivered? I guess maybe by a harpsichord or a string quartet. But then a bastard notion popped up to my head. It's like, would Beethoven have invented it at all? And I think he would have. But it was a striking question that got right to the heart of an interesting and more profound query. At what points in history did newly invented instruments find their way into the hands of phenomenally talented musicians? How did a musician of Beethoven's caliber react to a new instrument? How did Jimi Hendrix react when he first got his hands on a Fender Stratocaster? Where are these encounters in history? And were the inventors of musical instruments musicians themselves? If we try to trace the evolution of musical instruments back to their origins, we sometimes lose the trail of where they come from and who invented them. The same thing happens with music itself. For all the tomes written about musical instruments and music theory, the origins of music are still relatively unknown. Now imagine a bunch of early Homo sapiens listening to all the sounds of nature and trying to imitate them. After all, we still have hunters using animal calls, except now they aren't required to perfect them vocally. They can just walk out in the woods with a Bluetooth speaker, press play, hide, and wait for the kill. It takes no talent. And today, a talented vocalist sells out stadiums, but maybe back then, a talented vocalist could mimic and consistently attract prey. In the beginning, did music evolve to help us survive? Or was it a way to communicate with gods? Hunting rituals, harvest rituals, spiritual rituals. These are all possible explanations for why music came to exist. But in the end, no one knows where music comes from. And it turns out that the historical relationship between makers and musicians is similarly difficult to trace. But there's one fantastic example of a maker and musician whose virtuosity and inventiveness changed the world of music forever. Pantaleon Hebenstreit was employed as a violinist, keyboard musician, and dance instructor in Leipzig. He constructed, developed, and mastered a unique and large version of a hammered dulcimer in 1697. In 1705, he traveled to France and created a sensation with his unique instrument and playing. Louis XIV was so astonished by his performance and the instrument itself that he ordered it to be called the Pantaleon from then on. This was quite an anomaly at the time because the hammered keyboard instruments were not nearly as popular as plucked string keyboard instruments. The harpsichord enjoyed huge popularity in the Baroque period, but by 1709, an Italian harpsichord maker named Bartolomeo Cristofori thought it was time to update the harpsichord. He published a remarkable design of what eventually would become the pianoforte. The keyboard design principle was the same, but a series of hammers striking the strings rather than plucking them opened up a whole new range of possibilities for composers and performers. This transformed music performance and composition forever. And though conceived and born in Italy, the piano was developed over the next 40 years in Germany. The famous organ builder Gottfried Silbermann went through several iterations of the grand piano with a vocal and harsh critic named Johann Sebastian Bach, who preferred his organs. Now, a remarkable innovation to the piano by a maker named Johann Andreas Stein caught the attention of another musical luminary. In a letter to his father written in 1777, Wolfgang Amadeus Mozart wrote, "His instruments distinguish themselves by an escapement. Not one in 100 makers troubles himself about that. But without an escapement, a piano clatters and leaves a sound. When one presses the keys, his hammers fall down in the very moment in which they bounce against the strings, whether one holds the key down or releases it." In 1821, Sebastian Erard invented the double escapement action, which incorporated a repetition lever, also called a balancier, that permitted repeating a note even if the key had not yet risen to its maximum vertical position. This facilitated rapid playing of repeated notes, a musical device exploited by Franz Liszt. When the invention became public, as revised by Henri Hertz, the double escapement action gradually became standard in grand pianos and is still incorporated into all grand pianos currently produced. Still, no one knows where music comes from. But it is a clear example of a musician who invented his own instrument, performed on it, and inspired the creation of one of the most popular instruments of all time. Tonight, we have musicians and makers from Monad Studios and the University of Connecticut, as well as a trained architect and technology whisperer who believes in the power of technology to help people of all disciplines and ages find, express, and amplify their own creativity. But before we hear from them, I want to take a few minutes to introduce you to the technology that is empowering musicians, artists, architects, and everyone else to create their own printed instruments. Exhibit A, Concordia University student Caleb Laughlin. Now, Caleb wanted an electric guitar. He could not afford it. So he leveraged the university system, enrolled in a technology course to gain access to the 3D printer, and he downloaded STL files off the internet. He printed 4 pieces of an electric guitar body, added strings, wiring, and the neck, and he had a fully functioning electric guitar made with finishing processes in 24 hours. He also turned it in and got an A, by the way. Next up, we have the 3D printed metallophone. Now, metallophones are notoriously difficult to create even by traditional methods. And this was a project that involved researchers from Columbia, MIT, Harvard, and Disney Research. I don't really know who's involved there, but the point was they wanted to create a metallophone that was shaped like animals. And they did it, and they called it the Zulaphone. Good name, I guess. Yeah. This is probably the toughest saxophone of all time. The guys from Industrial Technological Research Institute in Taiwan 3D printed this saxophone from titanium, which is remarkable. And the printer they used was originally marketed for jewelry manufacturing, but it actually prints to, I think it's 50 microns, or the width of a human hair. So very fine, very remarkable. I'm not here to sort of cheerlead 3D printing all the way, though. If you actually see metal 3D printing in action, it takes quite a lot of sort of traditional bandsawing and machining to actually even remove it from the build plate. So it's not just, it's not a catch-all. It's not that easy. Next, we have 3D printed Indian tabla drums. This is interesting because you have a new technology being used to create a very old instrument. And this instrument traces back to around 200 BC. Next example is this. These guys are here. This is Monad Studios' Hornicopian drone pipe. And this is a really interesting example because it shows really what 3D software and 3D printing can do together, which is open up the field entirely to creating new instruments, which I thought was a very sort of interesting idea. That doesn't mean you can't do it with traditional methods, but look at that thing. It looks like a black wave being like thrown over his shoulder. We'll have a performance from Scott later tonight. Okay, God, 3D printed electric violin. So this guy calls it the 3D Varius, right? And his name was Laurent Bernadotte. And he spent years iterating in software and 3D printing, which is another fascinating sort of use that you could probably apply if you're a maker of instruments in a traditional way. You could probably apply that to your practice. But anyway, so he designed it over and over, and what his goal was to make it sound like a Stradivarius, which is quite a lofty and insane goal. And I heard the sound of it. It's not at all like a Stradivarius. But I applaud him for trying, and wish him luck in the future. I don't know what else to say about it. But it's very cool. And this is printed with stereolithography, and this is I'm sure most of you are familiar with 3D printing as fused deposition modeling, which is the thing that sort of looks like a automated glue gun. It just sort of spits out plastic in what looks like a little toaster oven. By the way, the technology in there is all the same. You go to a 3D printing show, and it basically looks like you have the same technology in the witness protection program. They all have different outsides. Okay. So, in conclusion, we may not know where music comes from, but I hope after tonight we'll have a better idea of where it's going. Thank you.
So my father was a composer, is still, and chef d'orchestra. And I grew up in a house where we had pretty much every single instrument that I never played. So tonight I will not talk about any of that. I'll leave the music to those who understand better than me. But I will talk about what I understand quite well, which is technology. And we'll start with a video that is quite high level and very visionary to kind of get things started.
I think that the divide between what's analog and what's digital is starting to merge. Our physical world is so unimaginably rich in texture and in depth, but until very recently, our digital experiences, for the most part, have been limited to flat, 2D impressions of reality. Today, innovative technologies like 3D printing, WebGL, virtual reality, and augmented reality are all redefining the ways we can experience and recreate the world around us. So what do all of these revolutionary technologies have in common? They all require high-quality 3D digital models. What does it take to make a 3D digital model? You can create a model from scratch, geometrically constructing it by extruding and revolving with NURBS, meshes, splines, and solids. It's a laborious process requiring complex software and high-end knowledge. Alternatively, you can capture the analog world as it exists. This can be achieved with specialized 3D scanners, but this type of hardware is prohibitively expensive and also requires immense technical expertise. Every day, technology is becoming more accessible and easier to use, but the difficulty of generating high-quality 3D assets has kept this trend out of the world of 3D. Until now. A new process called photogrammetry utilizes state-of-the-art algorithms to convert regular 2D photos directly into 3D data. With smart sensors that are now ubiquitous and new software that is exceptionally easy to use, anyone with access to a modern smartphone or a camera can now capture and create a high-quality, ready-to-use 3D digital model. What stories can be told when we can all digitize the world around us? For artists, being able to easily capture, modify, and recreate physical assets opens up a universe of possibilities. When we can sculpt any object, environment, or living thing, the entire world becomes clay in our hands. For marine biologists, it's helping them better understand the world's ever-changing oceans. For the first time ever, using photogrammetry, scientists can measure coral reef systems with astonishing accuracy. Not only does this enable us to document the state of existing corals, but with repeated scanning, we can actually observe ecological changes as they happen over time. The Buddhas of Bamiyan in Afghanistan were glorious statues carved into a massive cliff over 1,000 years ago. In 2001, they were destroyed forever when they were dynamited in an act of religious extremism. Like so many times in our history, an invaluable piece of human heritage had been lost. Except this time, we decided to search for the lost statues in a place that previously nobody would have ever thought to look: the web. Between Facebook, Flickr, and Google Images, there are thousands of photos of the Bamyan Buddhas taken by tourists through the decades and from almost every possible angle. Using photogrammetry and hundreds of these crowdsourced images, a team was able to digitally reconstruct the Bamyan Buddhas in a gloriously detailed 3D replica, one which now celebrates the story of humanity, of all of us together, preserving a vital legacy for future generations. In the near future, we will be able to digitize our entire planet as it exists in every moment. This four-dimensional impression of our world will enable future generations to literally scroll back and see what was really going on in this particular part of the world at that time. We'll digitize ourselves as well, giving our great-great-grandchildren the chance to see us the way we were when we were their age. By being able to better document our achievements, as well as our mistakes, we will help new generations build a future for themselves that we can't even imagine. Some stories are simply too big to be told by one person or one group of people. From passive listeners to active participants, we all have the power to take initiative in this frontier of democratized capture and creation. We're able to connect dots differently, to find deeper meanings in the patterns that emerge, and consequently, we're able to begin asking better questions. These new stories can be experienced differently, in all parallel ways, across time, across geography, across cultures, and most importantly, these stories will mean so much more to us because we were part of their creation in the first place.
To show you that this is not just a vision, let's take a look at a couple of projects. This is the common raven, the most intelligent bird on the planet. And lately he's having a lot of fun. He's basically focusing on the desert tortoises. And unfortunately and sadly, these images are very often to be seen in the California desert. The raven attacks the baby tortoises, and basically we are down to one last generation of tortoises. If we don't save this generation, this species in the California desert will be gone. Why is this happening? Because the ravens have explosion of population. They're about 50 times more than they used to be. And who is guilty? Of course, we humans. We create a lot of garbage. We destroy the habitat. We create a lot of imbalance. So who will fix the problem? There are two people who actually have a very good idea. Using technology, they thought they can outsmart the ravens. Those two people are Dr. William Borman and Tim Schultz from Hardshell Labs. And they said, let's make a techno-tortoise. Basically, making fake tortoises, placing them in the desert, and teaching the raven something better than what he does. How will they do that? They simply leverage the new sensors, which is basically super high-end quality cameras on your phone or just any pocket camera. They take a bunch of pictures of real tortoise shells. And then using the software that I'm helping them with, Memento, they basically create 3D digital models, and then they print. These are just some printed replicas. Which one is the true one and which one is the fake? Probably it's not easy to tell. And then the idea is to put a pressure sensor on top of each of the turtles so that when a raven attacks, it sprays something like a pepper spray that will not kill him, it's biodegradable, but being smart as the raven is, after 3 attempts, he will say, I'm out of here, man. I'm not going to touch this thing anymore. So that's really their idea. They opened a Kickstarter campaign because they're raising money not only to do this, but also to make the ravens, the tortoises move, like with little Arduino robots, etc. This is the very reason why I left architecture 15 years ago and then moved to being technologies, because I really wanted to be a part of a team that creates technologies to enable small players to play the big game. Bill and Tim do not have much money. A tortoise researcher, you can imagine how much that is paid or how much funding there is there. But leveraging technology, they are inventing the conservation preservation 2.0, and this is really beautiful. The next story is about Dr. Louis Leakey, who is the third generation of the famous Leakey family that for 3 generations and 6 decades has been operating in Tanzania and Kenya, basically telling the story of the human origins. They have found thousands and thousands of fossils of the first hominids and humans and animals and tools. And for years they wanted to share their knowledge with the world, but how? How many people go to Kenya? They are in the Museum of Nairobi, but it's not easy for other scientists, let alone for teachers who teach that, or for aficionados just to see it. So Louise was at TED, and she saw a photo booth in which we were demonstrating how you can use normal photography to create 3D digital models of the fossils. And she loved it, and she started testing, and she learned how to create beautiful 3D digital models out of the photos that, with very small means, and she herself and a couple of members of her team are doing to digitize the collection. And they started putting the collection online. The site is called africanfossils.org, and you can go there and you can basically start exploring. If you're a scientist, you can search by fossil number. If you're just a teacher, you can start looking, showing the kids how it looks like. And instead of asking kids to open a book at a certain page and learn about something, they can actually digitally touch it, explore it, look in the detail, compare them, etc. Louise and her team are also allowing you to download the 3D digital models so that if you have a 3D printer in the school or download patterns that are cardboard patterns to assemble them like a puzzle into the different skulls. This is an experiential learning. Instead of just from a book, you actually can touch it, you can feel it, you can compare, wow, this guy had a bigger brain, this guy was, So she is, in a way, not only archiving and salvaging what her family has been doing for 3 generations, but also introducing a new form of a much more interesting way to educate. The next story is about, the colors are a little bit faded out here, but yeah. It's a museum in Sweden, Mediterranean Museum in Sweden. They wanted to use tech to make kind of new experiences about an upcoming Egyptian collection that they were going to open. So they had this priest Nesvayu that they gave to us, and basically what the team did was made the tomography or CAT scan of the mummified body, and then the rest of the sarcophagi and the cartonnage we just took photographies out of. At the end, we ended up with 3D digital models of the mummified body, of the first of the cartonnage, of the first sarcophagi, the second, basically a 3D digitized replica of the entire artifact. And why did we do that? Well, they worked with Interspectral, a company that really specializes on this new type of interactive experiences on a table that actually was placed just in front of the glass behind which the mummy was kind of dusting. And this table enables you to basically digitally unwrap the mummy, slice through it, look into the finest details of every of the hieroglyphs or of the pearls, etc. And obviously, because it was 3D digitized, we could also make 3D printed replicas out of the sarcophagus. But there was something even more interesting. While they did the CAT scanning of the mummified body, they found 120 hidden amulets under the wrappings of the mummy. Without needing to unwrap them, we could actually print them and see them in real life. We actually printed a negative, and then they cast it in bronze, the amulets. Quite amazing, right? So these guys are introducing new experiences and tactile. You have a new digital touching, and then you have touching of something that you are not ever going to be allowed to touch unless you unwrap the mummy, right? The next one is closest to you. 2 years ago, we started a project with the Smithsonian. Needless to say, biggest collection of museums in the world, 19 museums, 137 million objects. Catastrophe, right? And for those of you who like going to museum, like me, you only see 2% because there is no space. You don't have enough buildings here, so a lot of the stuff is in storage rooms, etc. And a very smart, young, energized team in the Smithsonian decided there must be a solution to this. How can we show the collection that we have to the whole world? Not only those who come to the museums and see 2%, but everything to everybody. And also how to engage the kids of today who think that computers are everything and they find that, you know, museums are kind of archaic institutions, in their opinion. So this team started digitizing some iconic pieces from different museums. And at that moment, we met and we conceptualized together a solution that will bring museums on the cloud, accessible to everybody online. And this was a prototype that we together did. It's called the Smithsonian X3D, in which we started with about 20 iconic objects from as small as a bead to as big as a supernova remnant. And basically the idea was to put them in a browser and let people explore it while also following what the curators who have spent their entire lives with those artifacts can tell about those objects. We had a couple of rules. We wanted the objects to be as beautiful as in real life and not as in Second Life. Then we wanted to offer some tools that scientists can use, that curators can do for researching, for comparing, for measuring, sectioning through. Some objects are more interesting with what's happening inside than outside. Profiling, then allow curators to define hot zones and hot spots to add additional explanation and create tours on their own. So here is a little video that I made, but you're welcome to explore it on your own. It's called Smithsonian X3D. This is one of the 2 life masks from Abraham Lincoln. As you can see, you can change the setting, you can see it in 3D, you can explore it. Imagine you're a teacher, you're teaching about the mammoths. Instead of saying open book on page 130, you say download the Smithsonian digital mammoth and tell me how big was he, how tall was his leg, etc. But also we wanted to use these artifacts to make some fun, to make art, for example, a sticker for a t-shirt out of the mammoth, etc. This is my favorite project because this is a single cosmic Buddha unique in the world. And the relief was so shallow that it was not possible to read it. When we showed the curator that you actually can make the relief deeper just because it was digitized, he was sold, because this is where you see how technology today can help you research a little bit deeper, a little bit different, and present and explain about our past achievements or about details of our inventions in a new, different way. Obviously, again, because everything is in 3D, researchers are using 3D printouts in order not to touch the originals, but also using them for education. We even used some other software that is not for 3D printing, but for cardboard making, 1-3D Make, to make one-on-one crates for different objects just by making the negative of the object and then making the crate. This I personally made. It costed me about $70 and 3 hours of my time versus a couple of $1,000s of a crate for shipping or for archiving, etc. And this is all possible with these new ways of either digitizing or designing or making things. Smithsonian definitely paved the path of the future of the museums, the future of experience, the future of education, the future of curation. So this all sounds very simple and easy, but actually when all of these pioneers started to do that, realizing the opportunities of the technologies, it was very difficult. They had to learn super many software that they, as curators or scientists, I was like, I'm not a mechanical engineer, I cannot use this. It was a very difficult process and very complex. This leads us to the idea, by working with these people who knew what they wanted, to create a product that we call Memento, that basically enables you, either from photos or from laser scans or structured light scanners, in the most easy way. This is shown with photos. You just take a bunch of photos, you load them in the software, and then the software converts them into a 3D digital replica. At first, when you receive it, you receive something like this, and you say, wait a second, I took photos of a sculpture and I got that mess, but actually the sculpture is in the middle. Obviously, the photos did not know how far to go, so they were just capturing everything. But then we made a bunch of tools to really easily clean up the environment, then close the holes, so if you want to 3D print it to be, so it's like a 3D Photoshop, making 3D photography, but then that photography can be turned into the real world back through CNCing, through 3D printing, etc. So why does this matter to you, and how does this relate to anything that you came for here tonight? Well, all of these pioneers have recognized the new opportunities opened with advanced technology. In particular, with the following trends. The trends of ubiquitous sensors, the trends of new ways of fabrication through CNC to 3D printing, and the trends of the powerful 3D web and augmented reality, mixed reality, smart mobiles, etc. So what do I mean by ubiquitous sensors? Well, we live in an age of sensors. Sensors are any photo camera on your phone, on your iPad, on your pocket camera, a big camera, something that used to cost a couple of $1,000 camera. Now that quality sensor, you have it on every phone that you guys have here in the room. But there are also other types of sensors. There is something that we call structured light, which is basically photo with a projector, and then laser scanners. They vary in price, but they all have the same trend. They become cheaper and better. So they become ubiquitous, they become accessible. The second trend is about the new way of making things, the new fabrication methods. For a long time now, digital fabrication methods have exchanged the analog method of cutting and chopping, etc. We have now what we call CNC machines, computer numerically controlled machines. They usually require a digital file to make something awesome. And the one that is most famous is obviously the additive one, the 3D printers. And 3D printers are not interesting because, hey, you can buy them and put them at home and make plastic ducks and iPhone covers. How many of those can we make? But it's more interesting because you don't need the knowledge to use them. They are affordable. They allow for distributed manufacturing, meaning that they can be in many places in the world, and instead of I design something, I want to make it, I have to order it from China, from America, from wherever, it can be locally made. But most interestingly about additive manufacturing and 3D printing is that complexity comes for free. A printer does not care if you're printing a box or if you're printing something super beautiful, just like what you will see later being done. And this now leads us to the fact to understand that until now we have been designing for subtractive manufacturing method. Now we have the opportunity to revisit how we design things and to start maybe designing with algorithms and leveraging the fact that these 3D printers can print very complex structures. So something like a bike stand can be much, much lighter and much sturdier if it is made out of lattice structure, but that was not possible to be done until now in the ways we were manufacturing. So this has a huge impact on the world of design. And the last trend that I spoke of is the 3D web, the WebGL technologies, the Oculus Rifts and Microsoft Lenses, and all of these new ways that allow us to experience in a new way. So to conclude, scientists, researchers, curators, doctors, designers, artists of all kinds, they will have much more fun in the future. They will be able to push their professions to new limits that they never thought they could do. And this concept of, which we call rip, fix, burn, rip the reality, fix it, mix it, change it, and then reburn it back with 3D printing or CNCing, or rip, fix, learn, educate in a new way, teach in a new way, experience in a new way, I believe will affect every aspect of our lives. Thank you so much.
Well, thank you for your attention. I'm Robert Howe, and it's a great pleasure to be invited here on behalf of my colleagues in the UConn Digital Musicology Group. Before I go any further, I'd like to thank the people who have helped us with this project. And besides those many people who are listed here, I have to also mention Greg Case and Jeffrey Emmerich of the Coast Guard Band, and Ian Jackson of the University of Connecticut for their help in play testing the mouthpieces that we created. This is my second appearance here at the Madison Building, the first being at the American Musical Instrument Society meeting 6 years ago. Then as now, my talk concerned the study of antique woodwind instruments. That time I was talking about the Baroque oboe, and now I'm talking about the early saxophone, and the relearning of the techniques necessary to play them in the fashion of their time. This is a whole field of music study, the so-called period music movement, and it's one that I'm very involved in as a sort of an outside talented amateur and student. So I'm interested in woodwinds, and a woodwind is typically blown with a reed. The mouthpiece and the attached reed are the key to understanding the woodwind, how it sounds, how it behaves acoustically and musically. For the reasons shown on this slide, period woodwind artists have been hampered by the lack of specimens with a lack of data on the construction of early mouthpieces and reeds. For 40 years now, we've been reviving the Baroque oboe, but we still are not completely sure, for example, how the players of the day made their reeds. Looking at the earliest saxophones, we have a substantial number of specimens, at least 100 that are in playing condition. In my own efforts playing these instruments, one notes a very profound effect of the mouthpiece. In these two specimens, the tenor plays very well with the original mouthpiece, which we're fortunate to have, but no modern mouthpiece, even those that are said to copy Sax's designs, have been suitable. So I wrote to the guy that sells the mouthpieces that he says are copied after Sax's designs, and he says, oh, no, I've never seen one, but this is what I think they should be from what I've read. Well, he's doing the best he can. But, you know, as for the alto, on the right, I have found no modern mouthpiece which permits this horn to play at a suitable pitch that would have been at the time, nor one that permits it to play in tune with itself. And the antique mouthpiece that I received with it, which is not of Sax's manufacture, doesn't do any better than a modern one. And this tells us that Sax had some unique element in his mouthpiece design which has not been carried down to modern times, or elements. The surviving saxophone mouthpieces are very few and have not been systematically studied. Being extremely fortunate to have access to the tenor saxophone mouthpiece and the instrument with which it was built, I wondered if I could determine the characteristics that make it successful, if I could replicate it, and if one could then apply those characteristics to other species of saxophone, soprano, alto, and baritone. But first I wondered, is this a legitimate exercise? Is it correct to derive mouthpieces for other species from the tenor? And going back to first sources, Sax's 1846 patent for the saxophone displays the mouthpiece very prominently. It's shown thrice on the document, with the mouthpieces on the two specimens that are sketched being essentially identical. This one on the left is what we would call now a baritone saxophone, and the form on the right never made it into production. But he answered my question as to whether it was legitimate to scale them up and scale them down in his own patent application. There's the answer. Now, as a physician by day, I deal with medical imaging every day of my life, and I have an interest in ultrasound and CT, and I've been using CT to look at the fine details of woodwind manufacture. Micro CT, that is to say CT with pixel sizes in the micrometer range, 1/1000th of a millimeter, allows us to study objects with extreme precision. And of course, any CT allows us to view the anatomy of an object from any point of view without taking measurements and without doing anything that might damage the instruments. And just to clarify for everyone, what's the difference between X-ray and CT? The gentleman on the left is being subject to an X-ray. There's a plate behind him, and a beam is going to go through his chest and expose the plate. It's instantaneous, but it only gives you a 2D object, 2D view. The woman on the right, who's going to be subject to a CT, that torus has beams that are going to come from all directions around her, and then there are detectors on the other side. So just as you were displaying here with the cameras, we'll get a myriad of views which are then summed by the computer to create a 3D file that can be viewed from any desired object. So to do the work on the saxophone, I needed an expert in micro CT, and I was fortunate to find Dr. Sina Shahbaz Mohammadi, who is the director now of imaging at the Chase Labs at the University of Connecticut. And my advisor, Richard Bass, helped out also from musicological and administrative points of view. Then we were very fortunate that Sina's wife, Zara, who is also a mechanical engineer, was able to become our consultant for additive manufacture. We did some initial work on the instruments that Richard and I are holding, the curved English horn and the recorder, and then you can see that Dr. Shahbaz Mohammadi is holding the tenor saxophone in question with one of our replicated mouthpieces. In his micro CT work, Sina used the standard industrial equipment at two labs at UConn, and he performed our data manipulation. Here to show you how that's done, on the right, on the leftmost part of the right image, there's the X-ray source. Then in the middle, that orange-yellow thing is the tie on an oboe reed, and it's in a holder which will rotate 1,000th of a circle. Then a 10-second exposure is taken, then it moves 1,000th of a circle, so as to get that myriad of views that we need for the CT analysis. And then the detector is on the far right. Sina and I were then able to do manipulation and clarification of the data. We benefited very much from the advantages of microcomputed tomography. And the last one, of course, the last two are the ones that are of substantial importance to us in a saxophone mouthpiece. The internal geometry is notoriously difficult to measure, and we could translate it into some form for additive manufacture or computerized milling. The disadvantages of micro-CT, however, are not trivial, the greatest one being the limited specimen size. The largest specimen that our machine can handle is 10 centimeters in dimension, so we are obliged, for something as small as a saxophone mouthpiece, to take 2 views and then to stitch them digitally. You all should take this for granted. Here's how additive manufacture works. You take a CAD file, you create another file out of that, and you lay it down in layers. It's the creation of an object by applying thin layers of material one atop the other, rather than removing material from a larger block. So instead of taking a piece of stone and removing everything that doesn't look like a bunny, you take nothing and you add all the stuff that does look like a bunny, and you end up with a bunny. But the important thing is that it permits extreme precision and unlimited numbers of copies. This is a low complexity machine at work, probably making a bunny. So here's the foot joint on the left of an antique recorder by Cahusac circa 1750. And then there's a copy made by a professional recorder maker. And then there's 4 identical copies that Sina and I made. My daughter Catherine is going to pass some of those around for you all to inspect. Please understand that the joints she's passing around are early iterations, and that our quality control has gotten better, but they'll give you an idea of what they are. The 4 on the right are, they were produced just as easily as making one would have been. It's just a matter of telling the machine how many times to lay it down, and you can take a plate and make 100 at a time if you want. In our first presentation of this project, Sina demonstrated that the micro-CT and additive manufactured copies were actually closer to the original than the copies made by a professional recorder maker. And he also demonstrated by taking CTs of our copies and comparing them to CTs of the original and of the artisan copy, that the dimensions that are hardest to take by a craftsman, particularly the internal diameters of tone holes where you're measuring it at a deep level, those showed the greatest advantage for micro-CT. So the method had an error of less than 1% in all dimensions. It was within the error of my measurements. So here's the anatomy of a saxophone mouthpiece. And look particularly at the upper one on the left. It shows the tip opening. That's the place where the air goes through between the reed and the mouthpiece. And the reed has its excursion between the position you see and the tip of the mouthpiece. If the reed is too soft, the player's breath will just blow it shut and no sound will issue. Look in the lower one at the lay and the rails. You see those slender pieces there? Here's the mouthpiece from the B-flat tenor saxophone 39-116, and you see the surface rendering that we took by CT. Look at the detail that CT gives you. You can even see, you can compare the color on here where the grain differs, and that's picked up on the CT. Taking slices with CT is called a tomogram. It's a leftover term from traditional radiology. And here's some transverse tomograms from the saxophone mouthpiece. So in the center of that baffle area that I showed you, between the 2 rails, you can see that the inside, it's not spherical, it's not circular. It has a fairly complicated handmade shape. Whereas down in the shank that goes onto the neck of the instrument, it's perfectly circular. And the join between those two chambers is fairly abrupt. We could also see, and I don't show it here, at the very bottom, take the left image, the piece on the left, the tongue sticking up. At the very tip of that, there's a complicated anatomy of several curves intersecting, which is probably from the way that it's hand fabricated, that it hasn't been recognized by modern makers, and I think maybe part of what is unique about the Sachs design. I spent a few hours wasting time trying to take measurements by hand, and as you can see, you can get very, very fine measurements, but you can see it'd be very, very tedious to do that, and to turn that into a reamer to create a mouthpiece would be just prohibitively difficult to get accurate milling and creation, unless of course you use the digital method. So it made more sense to us to go directly to a computerized 3D source, such as additive manufacture. So Zara made a rough copy for us, and it's not shown here. And we were very pleased by its utility. It played okay. So we did, just like you were saying, I needed it. I was overseas and I needed it. So we sent the data to a company in France, and then they overnighted it to me in Brussels. And I had a working copy like 16 hours later, well, a day and 16 hours later. It just took no time at all. And the son of a gun plays. It plays wonderfully. It plays better than the original, which suggests that there may be either a bias on my part or a matter of the material that's being used, perhaps the latter. So, very pleased by these initial results, I measured the bore of each species of Adolphe Sax saxophone, soprano, alto, tenor, and baritone. And using tenor as 100%, I scaled the mouthpiece designs up and down to the relative bore sizes, and we created a family of mouthpieces. Katie's going to pass around some of the soprano mouthpieces, just showing how I made them at 76%, 78%, 72%. We tried different sizes until we found the one that gave us the best acoustical results on the instrument. When you study these, don't just look at them, also feel them, and you'll feel one of the flaws for this method, and we'll talk about that in a moment. So how do they play? You will ask, how do they play? Well, I have here Adolphe Sax Soprano 32194 from 1866, and I'm going to play it first with a modern mouthpiece and then with our Yukon mouthpiece. And I ask you to pardon my not having warmed up. This is the treat to which Anne referred, and the treat is that I'm going to play it for a short time. This is a Selmer mouthpiece from the 1990s. Yeah, this is the original instrument, 1866. Not quite in perfect condition. It has, you'll hear that there's a few leaks on it, but enough to make the point. There's a modern mouthpiece sound. Now with our copy here, this is very, the ligature doesn't quite fit, so it's a fussy thing to get right.
Was the other one edited?
The other one's called ebonite. It's a plastic.
Oh.
And it's been used for mouthpieces for 130 years. When that material became available, manufacturers abandoned wooden mouthpieces overnight because it's stable, and the mouthpiece, you know, is the part that's in your mouth, and it warps, and it cracks, and it chips, and a stable one is a good thing. That's not quite on fart. So if you'll pardon the left hand being flat. Yeah. No woodwind player is ever happy with his reed. It's a softer, more covered, mellower sound than a modern wood gear. And we were very fortunate to have the cooperation from our performance people at UConn. who gave up a week out of their lives to work intensively on this. I'm going to start this now. I hope it's not too loud. But this is the UConn faculty saxophonist and a graduate student with yours truly playing tenor, just for 20 seconds of a quartet from 1856.
They touch one, and it's like, an unbelievable honor.
So that's what they sound like. So the soprano worked fine. The problematic alto that I showed you before was tamed by the mouthpiece. It plays in tune, and it played at the correct pitch of sax's time, and I have a slide showing that. So here's the family we created. And this is a fellow that I just met at a music shop playing on one of my mouthpieces. And this is the problematic alto with the mouthpiece that I got with it, which doesn't work, but it plays beautifully at A438 with the UConn mouthpiece. The tenor, as I say, plays as well or better with the replica than with the original. And the baritone plays just magnificently. It sounded great. Now, there are differences, and this is why we do period music, is to find out what is different and learn from it and then be able to do it. The tip opening on the sax original, go back to that slide I showed you of saxophone mouthpiece anatomy, the tip opening is very, very small, about a third of what it is on modern mouthpieces. This requires a harder reed so it doesn't just flap shut, and a harder reed reduces the responsiveness of the instrument, but it enriches their sound. So the tenor and the soprano also required narrower reeds than are sold today. And I was fortunate to have a box of specialty narrow tenor saxophone reeds in my basement. I don't know why I had them, but I did. If you live long enough, everything you have will eventually become useful. And B-flat clarinet reeds turned out to work fine on the soprano mouthpiece. Now, the period saxophone world is a small one, and as word of our work got out, new mouthpieces came to the fore. And so I got some measurements just with calipers, not with CT. I was very pleased to find that our measurements for the alto and the baritone agreed within a few percent with sax's original. For the soprano, however, sax didn't follow his own advice. He didn't simply scale down the bass. He made a squat, wide mouthpiece, which of course works wonderfully, and which is more of a model for how things are done today. But it was interesting, although you can see my dimensions vary very much from the original, the volume contained within it is only 3% different. And that's a major factor to the intonation and pitch of the instrument, is the volume within the mouthpiece. So sax deviated from his own design, but his own design would have worked perfectly well, we think. There are flaws in the method, and if you've had those mouthpieces in your hands that I'm passing around, you'll find on the lay, on the rails, there's little irregularities, and this is stepping artifact with additive manufacture. Each time you have a layer end and the next one continues, it's like a little stepping stone, and so it's a little bit imperfect. Also, if you saw on the recorder foot joints that we were passing around, they're kind of rough and scaly on the outside, and that's the so-called grain artifact that distorts surfaces. We also find that one external surface, the one that's on the manufacturing plate, is perfectly smooth, and the other ones have these potential for artifacts. And one that's important, I think, is that copying something propagates any unrecognized changes that have happened in it. And just something we have to do carefully. We've considered the numerous directions for further research in this, but right now we're limiting ourselves to improving the mouthpiece manufacture and to getting our current work published. There's only 24 hours in a day, and we all have busyness. But it's interesting to find that there is a physician out in Minnesota who has done CT on a Stradivarius and broken down the images into individual parts, and you can get a copy of this violin made by CNC milling, which is actually put together by luthiers, not by gynecologists or radiologists, and they play perfectly well. There is substantial work being done on string instruments, which is, of course, where the money is in musical instruments, and and in some of the European labs. We were very fortunate that our work was published in our journal of first choice before we were even finished with it. And I think this is in large part because this is really something that required a university, not a conservatory, and not a technical institute. You needed to have music people, and you needed to have engineering people, and you needed to have imaging people to make this work. So it's part of the bringing together, I think, intellectually of the project. So in summary, we used micro-CT to create a data file of an Adolphe Sax tenor saxophone mouthpiece. We modified the data to create a family of working mouthpieces by additive manufacture. The method works, and with refinement, we will produce all of the mouthpieces we need, perhaps using CNC milling rather than additive manufacture. Groucho Marx, told us that it ain't over till the fat lady sings. The lady in the upper right is singing, and my talk is over. I thank you for your attention. Oh, there's two places you can find a longer playing of the saxophone quartet. If you go to Google and Google Yukon Today Sax Mouthpiece, hits 1 and 3 are two separate radio reports that we've had on this work that have the quartet playing at length. They're really nice.
Hi, I'm the fat lady. My name is Eric Goldenberg. I'm from Monet Studio. I'm one of the two components of Monet Studio. The other one is Veronica Salzberg, who's in Miami with our two kids. And I'm very grateful and honored to be here at the Library of Congress. Thank you, Andrew. Thank you, Anne, for thinking of us, and also for inviting Scott. And I would like to show you what, in a way, I'm going to focus, of course, on the music instruments and sonic installations that we've done recently. But there's a very long trajectory leading to this. I'm still myself trying to understand why we end up designing music instruments when I'm an architect. And Monet Studio is an architecture firm that does mostly experimental projects derived from computation and digital design. And I'm also a professor of architecture at FIU in Miami. And but let's get started. So in a way, just to put it simply, if I can, I want to show you why I think what we've been doing, or what this trajectory is about bringing the surfaces of architecture that usually surround us, but there's a certain space that they define, and we are a smaller entity within that space, as many as we may be. And I just wanted to bring all those surfaces much closer to the body. I think this whole presentation is about that, and the whole a big part of the motivation of doing music instruments is more like going into body prosthetics on my part, rather than the music, which I leave to my great partner Scott here, who's also a designer. And so this is the cover of a book that I've done recently called Pulsation in Architecture, which is my research on a certain obsession about rhythmicity or rhythm in architecture, the perception of rhythm or the sensate quality of rhythms in architecture, especially the kind of architecture that's cropped since the last 15 years or so, that's very much influenced by the digital technologies, where there's a lot of like topology and surface manipulation and such. Let me just try something. The image is being cropped a little bit. Just try something. Good. So I'm just going to run through just to give you a background of these kind of 15 to 20 years of my own trajectory in architecture associated with computation and advanced digital design. I'm going to just show you probably like 3 projects and then move on to what's interesting for us tonight. So this is a project that we were invited to participate in by the Museum of Modern Art in New York. They do these yearly program called Young Architects Program at the PS1 in Queens. And so basically, I'm not going to get too much into the architecture because you guys did not know that you were going to get any architecture tonight, so I'm not going to force it into you. But this is a project where I think it's for us, it was our first deliberate attempt to really investigate a lot of this idea of rhythm and rhythmicity and rhythmic perception in the architecture. And of course, there's the Astoria elevated tracks, a couple of blocks away from PS1. And everybody that goes to PS1 has to take this train mostly. So this is an experience that you really have when you're going to go to these parties that are held every Saturday with music and DJs and whatnot at the open courtyards that the PS1 Museum has in Queens. And so what you see here is a top view, a plan view of what's gray is the existing museum. Everything that's white is the open courtyards that there are that you have to traverse in order to get from the street to the institution. And basically, what we were designing is it's a large installation slash like large tent like structure that will also host these parties every weekend. And I feel like I have to go faster through this. But what you're seeing is, I think this image is key in that the way it's about perception, because the way, this was probably 2008, and I was trying to photograph the train tracks very quickly because there were cops that didn't like you. I mean, imagine a guy in New York taking photos of the train tracks for a long time and the structures from beneath. And really, they grabbed me and they had me. Luckily, they didn't take away my photos. But what I like about it's not that, it's that the fact that they're rather big, right? So in order to capture all of that, they had to, where there wasn't any kind of technology such as panorama or Stitcher in the camera, I just took many of these photos and reconstructed like Hackney does, right? So I actually like that technique, and I was using creatively that technique all the time, and the result is you don't get the kind of smoothness or the continuity that the real train tracks have, but you get this kind of faceted, disjointed sense of continuity, which nevertheless provides the sensate. What you actually see, your psyche associates this in a way to the way in which you perceive it, but it's completely different, of course. So we decided to do our project in the same manner and actually start with something, because this competition has a really low budget for young architects, and we were very interested in curvature, and all that you see tonight is a lot of curves and topological surfaces. We wanted to convey that but in a very simple way with faceted surfaces. So I tried to do the same thing that was done to do the photographs, but instead of a post-operational procedure, to really start with that. So this project is the aggregation of a series of modules that they are rhythmical, but every single component of that rhythm changes, right? So it's kind of modulated rhythm, and there's a basic component for the space that that is repeated, but no single element that form part of that component is equal, because there's kind of the distortion of the overall movement, right? So it's about different speeds of perception. There's a part where you go through underneath. There's a straight trajectory from the street into the museum. They just kind of bypass this project. Or there's another part where there's these kind of lounge pools and areas where there's much of a loungy, like slower perception. That's kind of that space. And there's all these cuts that are produced by the rupture between the modules of the rhythmical module of the project. Through those cuts, you can traverse these two realms. So that would be an aerial view of the project. This latches onto an existing wall, and that would have been, we didn't win, we came in second. Fortunately, the winner only is the one that gets to build it. But, so, as I was saying, this talk is kind of like about the body. So we were obsessed with the segmented animals that have segmented bodies, such as the lobster, which was really, we were trying to see what kind of intelligent logic is there in the body of that animal that we could appropriate or hack into to kind of produce this kind of rather large architectural body that you could inhabit, right? So this is actually the structure. Underneath that, anyways, moving on to the second architecture project that I just only want to throw in as background. I'm not getting into it too much. This is a project we did for my hometown from Buenos Aires, Argentina, for the Port of Buenos Aires, and it's a project for a large performing arts center, much larger than the previous project, right? So I'm going to go upwards in scale in the architectural projects. And this one really was trying to first observe and understand and index effects of turbulence in liquids, and see what of that could we also appropriate for architecture and produce this project that is set in a way that it's really on the wharf, on the main wharf that gives access to the Puerto Madero, the main port, which is a former industrial port transformed into a kind of cultural office area in Buenos Aires. And this is trying to set kind of a first layer between the river, the large river, Rio de la Plata in Argentina, and the port, where it's kind of like a second horizon, where this kind of rhythmical progression with distortion is set up. And in that sense, architecture has a lot of inherent repetition within. Just look at anything in architecture, from facades to the modulation of that wall. You know, it's really, anything has to be panelized or done in components. There's no single surface that will be, you know, that big. So taking on that given situation and then using that as enhancing that as an aesthetic and perceptual device is what these projects are doing. Again, I'm just bypassing a lot and moving through it, but what it was also doing is kind of offering itself as more as a landscape rather than as a building, and counterpoint to existing towers that kind of punctuate the waterfront of the city of Buenos Aires. So this becomes a very democratic, very open surface that people can, the roof of the project is accessible for events and things like these. So the whole geometry with all these pathways and all these gangways is meant to bring people into those surfaces. And in a way, it has several kinds. There's this kind of very convoluted rhythm of juxtaposed ramps and whatnot that bring people in. And then there's a very kind of repetitive, but with variation, linear rhythm. There's that set horizon, right? And then this is kind of drawings that we do and part of the architectural stuff. I mean, I naturally call this architecture. I'm not sure that you think this is what you normally associate with architecture. I don't see much of this in the skyline in Washington, right? But maybe soon. So moving on with this, just for you to get a grasp that what you will see next is sort of coming from somewhere and not from music, right? So that's the reason I'm throwing it in today. Of course, you know, our perception of rhythm, I think, goes hand in hand with the notion of sensuality and music in itself. I mean, it's probably legacies. I mean, lots and lots of books that speak about this beyond my own capacity to look into. But we find this idea of rhythmic progressions also in many formations in nature, such as the strangler fig trees, which, you know, are everywhere in Florida, which are fascinating and also very time-based processes which you can observe on the roots of trees that grow over existing trees and, you know, kind of cohabitate and kind of fight for nutrients until 200 years later, maybe the host tree takes over and exhausts the parasite trees, takes over the host tree, and you get this kind of open lattices of depleted structures, right? This one right here, which are absolutely wonderful and beautiful. It's kind of, I think I'm giving away a lot by showing you these images, because then everything else you think is just replications of these, right? Anyways, yeah, that's the only thing we do. This is a trick, as the gentleman I presented before had his own trick. Our own trick is, only thing we do is we've been copying this stuff all over the place. The other project, the last project I'm showing, which is this, is growing much more in scale. This is a project it's a memorial for the victims of the tsunami that happened in Thailand a few years ago, and it's 300 meters long. It's an international competition, and this is part of a much larger jungle. The project was on a site that had a very small drainage up on the right, small drainage channel that went down about 25, 30 degrees down towards the beach. And what we did is we decided, in order to do a memorial for such a dramatic event, to really make a landscape project that was like a collection of courtyards, and that these courtyards would line up, stringed by this kind of drainage channel, which we enhanced, and so we made the presence of water part of the commemoration of the dead, right? So, and also what you see here is many of those courtyards, and the green that you see is just the kind of interstitial spaces between the courtyards where kind of new ecologies will grow, and new life will be cultivated, right? So, in any case, it's a project that has a lot to do with repetition with variation played out throughout. There's no two single instances that are the same in which these courtyards are laid out, but rather it's a collection of multiple possible variations out of a very simple initial unit, which is this courtyard idea. And then ultimately it has some, this is the layout. You see these very long paths, and there are some canopies that hover over these courtyards. And then there are those places where kind of new natural growth happens. And going further into the details, this is typically how we proceed. We, kind of excavate and give much, much more detail. These canopies are also large pouches that collect water and kind of redistribute it throughout the project. So all these kind of tubular tubes that come out of them that bring down water. They also become railings, and they also become pathfinding elements throughout the project, right? So there's kind of an effect of synthesis in that way. And in this project is this idea of the kind of second device that latches onto its host and becomes one with it symbiotically is present. So I'm just laying down some of the tropes that are constantly part of what we do when we do architecture, that are there, so that we kind of can shift now and begin to look at some of these things that we have built recently. So that was growing in scale, and now we're going to go down in scale significantly. This is a project that was commissioned to us for the Metropolitan Gallery on one of these recent, very large 3D printing conferences, which has some of these conferences have an art section and a fashion section and whatnot. So as an art section / architecture section, we were invited, and we did, we produced a structure that I don't know yet what it is. Honestly, I just don't know that it has any use. And it's also not a sculpture, but I guess some people will call it a sculpture. It's mostly an exploration of rhythmical ways in which you can embed different kinds of rhythms within other rhythms. This project was done also combining two digital fabrication technologies. One is CNC milling, and the other one is 3D printing, fused deposition modeling. So what you see here is this larger kind of element, to call it something, then receives another layer of smaller rhythms that are embedded within some of these cavities. This was one of the first times that some of those more conceptual and more speculative architecture projects had the chance to be explored in, of course, very reduced scale. But the reason I wanted you to see those architecture projects first is because now exactly the same techniques that are used in 3D modeling, we use a software called Maya from Autodesk. In the same way we think about those projects now is in a way it's a scaleless problem. You can shift scales with no difficulty at all. Even some DNA types of lines and moves and surfaces used for a master plan you can use for a door handle, right? So we definitely take advantage of that. But it also, along the process of doing that, you discover effects of materiality and effects of machining and programming, how you want the machine to cut certain materials. But in the case of the CNC milling machine, the way the machine operates as it moves by, sculpting away from a solid piece. In this case, we use a high-density foam for that. leaves a certain scoring of the passes, and you can play around with that, play with different kinds of ways to produce texture. So I guess this project was a way of, in a way, I guess the first time that I showed or that Scott saw this, he told me, but that is a music instrument. I said, what the? I mean, I can't say that, but you are absolutely right. And I think we were communicating with Scott. This was probably, 3 or more years ago. There was a previous version of these where that conversation took place. And then at some point he came to our studio in Miami, and he brought other things. He's kind of like a strange person that has, I mean, he will play that, and he plays like a musician, but he also does any number of other wizardry with things that you wouldn't think is coming from a musician, but he creates absolutely gorgeous music out of something like these. So he saw the opportunities, and I guess what was present in the project, inherent in the project, was all this kind of experimentation with your kind of sensual understanding of rhythm, intuitive understanding of rhythm, which is coming from us. And so this project had several different iterations. The last one, it was kind of more like a coffee table, elevated about about 4 feet from the ground. And so it had an upper surface and a downward surface, an undercarriage of sorts, which sort of were the same, but then the undercarriage developed the legs, and it was kind of much more interesting in that way. And in that case, again, combining just playing around with different fabrication technologies, the legs were 3D printed. So they were, in a way, like, the project was kind of on stilettos. And when this was put in that exhibition, everybody was asking, so can I sit on it? No. I mean, are you crazy? And what can I do with it? I don't know. I mean, it's there, right? So just feel it. So, and that is the reason why I think it's not clear to me what it is, because I'm not sure it is something of that scale. In my mind, maybe this is a large, again, a performing arts center, and you're underneath it, right? And those are the big columns that are supporting it, right? So in a way, architectures, all of the stuff that we've been doing that has to do with product design and with objects is very impregnated with our ways of thinking and conceiving architecture. And then you can see how those legs are really picking up on some of the main lines of articulation of the longitudinal rhythms of this project, and bringing it down to a much more detailed point that receives the structural weight of the project and transmits it to the ground. Ultimately, this is what the upper surface looks like, with all these sort of nestled different scales of rhythmical progressions. And this is probably my favorite image, where, I mean, one thinks that, okay, 3D printing or CNC milling is about pushing buttons and transferring digital information to physical constructions. There's much more kind of craft involved, handcraft. Like in this project, there was a lot of selective sandings to kind of be able to leave that certain kind of scalloping in some parts, and a different kind of scale of scalloping in others. So playing around with how that would relate to then the uppermost layer of repetitive 3D printed components. So there's a lot of investment to obtain those effects. And when we sent these from Miami to New York, what we sent along with it was a mirror surface that would also reveal what the undercarriage was like. And as you can see, this is a rendering, it's not a photo, because of course it arrived completely shattered. So we learned to, have it cut locally, have a mirror cut locally. So that was kind of playing around with ideas of symmetry in more than one way. And like I said, we had no use for it. So I guess it was something about the body, right? So definitely about the body. That gives you the idea of how big or small that was. And for, I don't know for which bodies or what, this is, what you're seeing here is we play around a lot with imagery when thinking about projects. And we were commissioned to do another project for a gallery called Design Matters in LA. And this was a great brief that the curators of that show had, which combined sci-fi, architecture, and eroticism. So perfect, down our alley. So that seemed to be things going back to Geiger, right?
Right.
This project, I think, is the first one we really began to interact with Scott in terms of long-distance conversations about the possibilities of bringing sonic components to the architectural installations that we were doing around this time. And at the same time, the curator asked us to sort of get some images out so that they could do their campaign to raise funds for the project. So our first, while we were developing the actual thing that was going to be built, we created this kind of affect-like imagery that would tell the story of this project. So I think these are possibly the best images about, if not that one where I'm underneath that project, to tell about the relation, the kind of prosthetics, the way in which we begin to think about in terms of prosthetics when we think about music and producing objects, instruments. So that's kind of a facade, a view image of what the structure that we thought of making, which was ultimately not made, not yet, at least not yet, which was basically speakers. Your typical Marshall stack of speakers is a vertical condition. We thought of kind of tumbling down a speaker and then holding that at a certain height with a kind of one of these typical structures that you've seen us made before. And since those are tubular and they look like roots, we thought those would actually be an optimal opportunity for wind instruments to be part of, for the wind conduits to be part of this kind of complex instrument, which will include ultimately a DJ, will include Scott sitting on this and playing some strings and blowing on it. And that's a top view of that. And so it'll have two types of output for sound. One will be kind of multi-directional surface of the grill of the speaker. That will be the directed sounds coming out of those tubes. And we just went through with that brief. We took it wholeheartedly. So again, but we take these things kind of really. We think it's important to kind of convey the sensations of what you're working with, and that the architecture and the ways in which the body could potentially interact with architecture are absolutely interesting, at least fascinating for us. And these are some of the typical tests that we do at our office. We have these MakerBot machines and whatnot. Also have a lot of those at FIU, where we have a lab where MakerBot has provided a machine so every two students can share one. We have like 38 machines or so. So it's great, it's a luxury. And so these are smaller prints. But then also playing around with these images that we were asked to provide for in anticipation of the show. We thought, okay, we're going to keep playing around with the scale of the object, and something which was large enough to hold 3 or 4 bodies. We reduced it completely and snugly applied it to this body, and that was kind of an intuition of what could be possible in terms of prosthetics. It's kind of not yet trying to produce an instrument that way. We're just envisioning something that we did later. But for that show, that is the scale that was meant to be. And that's more details on that speaker, and that's kind of further work on the project, and the project gets refined, and at some point you begin to develop the logic of how you're going to produce the parts of it, and the logic of assembly of it, and that's still going on. But anyways, those are more detailed images of it. What you see, kind of translucent surface we're looking from the top down, is the surface of the speaker, which is that. And then you see this higher surface here is where at the height of a DJ can operate their gizmos, and that's that project. Now, this is really the first, in effect, project where we were able to collaborate with Scott, and we also created a guitar for it. So that's really the first product of our collaboration with him. But this is a mural that was created it's a sonic mural, really, created for Miami Beach Urban Studios. There's a really cool gallery there. And this is about 18 feet long or so. And what the thought of this was to create a piece that would, again, it kind of host to the component, which is the music instrument. The guitar would have two possible positions, either on the left or on the right, on the extreme right, left or extreme right position, where the guitar can actually be docked, and it's exactly the negative form of the guitar that receives it, and you see it in here, there on the left side. And the musician, Scott, picks it up and plays it and docks it in. Any number of feedback experiments can be played while the guitar is in its place or played. And that is our friend Scott. So this is probably one of my favorite images ever of Monets 2 here with Scott playing like this. And that guitar was actually done with a CNC machine. It's not a 3D printed guitar, it's a milled guitar. And what you're seeing here is a separate unit, which is the neck, which Scott typically fabricates the functional component of the guitar. And we worked, in consultation and collaboration with him to design the bodies of the guitars at our office. But this mural had several sonic performances. One of them, I'm going to play a little bit of how that sounded, is that those curves and the variation of the topographies of the curves were done not just an aesthetic device, but also as something functionally that could be played with these transducers. So through these the transducers are just none other than speakers without the cone, right? So the transducers can reach, you can measure any frequency of any object, and through the transducers you can get some sort of reading of that. And in this case, they were feeding a certain composition through a laptop, through the transducers to the surfaces, and according to how they were gesturing over the surfaces and finding sometimes some deeper cavities on the surfaces, then the sound will be amplified in different ways, right? Finding the cone or not finding the cone as they move through the cavities. And you see some more images of the guitar. And critically, also, these surfaces had that scoring or that texture of the CNC milling machine. And that's really the very texture. Some parts have heavily textured, some parts are much more smooth. And that's by choice, how you sand it as an after effect. That's at the end, Scott and the other composers played all together. What is interesting is that these surfaces, which are generated from a kind of architectural sensibility, are there to now for the first time, for me at least, the architecture is not an inert, passive surface, but rather this surface is able to partake on the music effect, right? So there's a direct effect and a direct, let's say, direct consequence on some of the grooves and some of the variation on these gestures. But what's interesting too is if you were painting, you would do gestures of these size, right? So there's a kind of a scalar, very interesting scalar relationship to me between the body, the scale of the gestures, and the real gestures that take place when they move over it, right? So that's a detailed further development of the guitar. New versions are done constantly, trying to perfect it, smoother body, different kind of neck. This is a monobar sitar. Scott could tell you much more about it, but it's something that he created as an instrument, which has this kind of single string that is a different version of it. It's a bass guitar. It's a treble bass guitar, smaller. So that's kind of that mural, and I think this is probably the most iconic of the instruments that we have done thus far, and probably the reason why we're here ultimately. And this is a 2-string piezoelectric violin that we created, where this kind of exaggerated size of it in these renders that we created at the beginning, ultimately is much smaller. But what we do when we create these instruments, I think this is part that I'm really getting excited about. The more we do them, the more we create also other types of instruments, is that it has a lot to do with not only with posture and just understanding how musicians need to play, or how to best suit their habits, the different habits of that are necessary for each musician. But also, it does, in working with these instruments, what we're doing is we're creating another body, right? So the guitars literally have bodies. Only one of these string instruments have bodies. But what we're doing is kind of a kind of volume which surfaces are there to kind of interface between the body of the human and what's necessary to perform with it, right? So for us, I think that's the kind of the more interesting opportunity for the architectural exploration. And as you can see, I mean, I could tell you that this is exactly, or not exactly, but it has the same amount of geometric information there was to produce a very large performing arts center, except it's all concentrated on something that has this dimension, right? So that's to me the interesting point, the interesting opportunity, having done, let's say, 15 years of those very large projects, which are way bigger than what you can even look at when you try. And then all of a sudden it's all concentrated on one discrete device. And that's more images of the violin. I'm gonna just, I think this is the right image to tell you where we work in Florida, right? It's kind of, it's very lush presence of nature around it. So I think that the images speak for themselves in terms of the violin, and we've done also a one-string piezoelectric cello, monovioloncello, which is there along with the violin. And I think the other part that's really interesting is that all these instruments, for us, have their own constraints, not in relationship to how they need to interface with the body, but about the other components that are in it, which always is a process of feedback with Scott. We get a lot of back and forth with him in terms of accommodating for what's necessary and finding, in his case, very creative ways of alternative solutions to be able to fit these geometries, but also to be able to be effective in terms of the performance needs. These are details of the violin. We also created, by the time, we created like 5 of these instruments at once last April for another show in New York. And we also created for them as another different version of what was then a 2-dimensional, 2.5 dimensional mural. This was a fully 3-dimensional spine / rack of instruments, where 5 of these instruments will be again mapped on, latching on, and in the front there are the 3-string instruments, the violin, the treble bass guitar, and the cello. On the back part there will be 2 wind instruments, one of which you saw an image of Andrews before. And this was built. The pieces again is high density foam structure done with a CNC milling machine, and all the instruments, these 5 instruments, 4 of them actually were created, the 5th is in production, are all 3D printed. All 3D printed with common MakerBot, nothing too sophisticated in terms of printers. And they played, and we've been playing them not only in New York, then throughout the summer we went to Japan, to China, to Russia, to Prague as well, and Washington, right? So that's kind of an image of the mapped out instrument onto the topology of the surface, so that there's nothing to hold it other than the form itself. Sure. And I just run through the last images. That's more on the guitar, so you get a sense of and that's the cello. I think that there's a lot of interest in bringing to these instruments the sensibility of those structures that we found in nature. And in terms of that, I think this is the most interesting one, because it's the largest one, is the one where the whole way in which you're going to hold this instrument is not trying to map out an existing standard instrument, but we call it hornocopian, but it's actually a very large didgeridoo that coils around the body. And you saw it before, that's Scott playing it. And I think that what is interesting about it is really, in terms of scale, is mapping almost 1-to-1 the size of the roots and the branches of the trees that originated them as triggers, image triggers. I think that the last things that I'll show you is a couple of other projects. This is the 5th that is not yet built. We're still adjusting it. It's getting more and more interesting. That's another one of these didgeridoos that is in production. And this is being printed as we speak, which is a 6-string electric guitar, and it's the last instrument that is in production right now. And I'm happy now to let you hear Scar, because I'm gonna play everything.
you so much. It was interesting to see how this evolved out of architectural buildings, rhythmicity, and into an instrument. And it's exciting to see this kind of a panel of people who are doing this every day. I really want to thank you for coming. I'm sorry about this, but thank you to all our panelists, and thank you for coming.
This has been a presentation of the Library of Congress. Visit us at loc.gov.